This is to me maybe an example of an active solid. What you see is a bunch of starfishes, and actually these animals have no brains, but they are able to move around in incredibly complex ways on the seafloor. That's what you see here. And I guess to me it's really, if you view that as a material, which I think I'm very much inclined to, for instance, what you see here is really traveling patterns of the feet of the starfish. And I guess the question you might want to ask is, okay, if I want to engineer materials, like most materials of today, once you make them, they have a pre-programmed response, or even robots, they have a pre-programmed behavior. But this active solid here is able to exhibit incredible adaptivity to the environment, to changing conditions and so on. It probably maybe is even able to learn. And I guess the question I want to ask is, what are the principles I should embed in a synthetic material if I want to, get anywhere close to something like that? Okay, and that's what we do in my group, and we do that mostly by actually breaking reciprocity, as was extensively discussed. And today I want to show you two results that I think maybe help us go in that direction. The first is on solitons. What you see here is a bunch of slightly more evolved versions of the Legos of Vincenzo. What you can see here is that you can basically send you basically have an endless domino effect. So you can send endlessly trains of solitons and anti-solitons. And on the right, you have an example of an object that not only is non-reciprocal, but somehow its purpose, its function emerges by virtue of an interaction with the environment. And so what I want to argue in this talk is, like non-reciprocity is great because it somehow it makes, it has an arrow of time, and it leads to dynamical steady states, limit cycles. But also, often importantly, the purpose, the functionality actually emerges via nonlinear forces, nonlinear interactions from the environment. And if you want to think about active solids, it's actually crucial to also think about the latter. If time allows, I will also show that you can also do some learning in those materials, but I'll get there, but I can talk about it later. Okay, and so solitons. So this was done by a PhD student in my group, led Jonas Venstra, who has led actually both work. Like if you look at the starfish or even these millipedes, actually, at least I can't help but see like these traveling patterns as nonlinear waves. And actually, people who start to mimic that also use this kind of idea of traveling pattern solitons in that object. But if you want, the argument is that the way the solitons are created here, the ways are created here, is very different from the ways the solitons are created here. Here, you actually need to constantly drive the soliton with a magnet underneath. Okay? Because the physics of solitons, of driving solitons that actually is out there, is driven solitons. So pretty much the physics of toppling dominoes, right? Which is basically a soliton equation, a wave equation, equals some damping, and basically when you drive your soliton, you just tilt the potential here such that the soliton, the state cascades from the metastable state to the stable state. Okay. In my group, we actually also play with that a lot in the context of dissipative metamaterials, and that allows us to make materials that exhibit some form of basic machine-like functionalities or even absorb shocks very efficiently. Okay? But still, in all those examples, I always have to drive the soliton. I always have to keep on pushing. This is not what the starfish does. This is what the starfish does. It's, it's spontaneous. The solitons are spontaneously kept on being sent and followed by trains of solitons and anti-solitons. So I guess the question I want to ask is, how do you actually do this? How do you reach basically this endless domino effect? And the answer to that question, or one answer to that question is non-reciprocity. So what we have is as I said, the slightly more elaborate version of the Legos of Vincenzo. You have two motors that have sensors, actuators that can communicate between them. And here we attach, or we tell, they have a rubber band between them, and also they have a magnet that makes it such that you have two stable states. The pendula are tilted left or right. Okay, and when you do that, you see that you can switch on non-reciprocity. That means that if you tilt the left arm, it makes the right arm tilt, but if you tilt the right arm, it doesn't make the left arm doesn't move. Okay? Great, so we have our non-reciprocal bistable building block. And now we can deploy it. So I guess that's a summary. So we can deploy it, we can look at the chain of those and study the propagation of kinks and anti-kinks. Okay? So let's do this. We put many of them together, and then indeed, oops, my movies are a bit out of sync, but you get the idea. You can send continuously pulses of, this is a soliton, the one before was an anti-soliton, so you can continuously send them forever and forever, okay? And so this is quite unique in the context of, in the context of driven soliton. This is a result I hadn't seen anywhere before. Usually, when you have a sheared medium, like a dislocation that moves, if you shear in one way, the soliton will move one way, but the anti-soliton will move the other way. Right? So whenever you drive a system, you drive solitons, kinks and anti-kinks will always move apart. They will always move in the direction that's dependent on their topological charge. Here, regardless of the topological charge, the solitons move in the same direction. Okay, so that's kind of distinct in that sense. If you want to model that, what you could do is, take a basic canonical equation for solitons. So here's the Frenkel-Kontorova model, which we have here, which is basically a multi-stable potential, elasticity, and here the non-reciprocity. That in the context of fluid dynamics, it's maybe a bit hard to look at discrete equations, but we can always cos-grain it, look at the continuum limit, and what you have is a sign-Gordon equation, which basically is my sign-Gordon equation here, plus some term on the right-hand side. And what you see is that you have damping, but here there's a new term here that really comes from non-reciprocity, that's an advective term. So I guess the argument that non-reciprocity emerges also whenever you have advection is something very generic that people like Nikta exploit a lot in the context of microfluidics or biophysics. Okay? What we do now is we just say, okay, let's go on and try to analyze this equation. So the nice thing is, okay, even though this term I hadn't seen anywhere in the literature, you can still use the machinery of soliton physics to actually solve that equation. In that context, it's an integrable equation if you have sign-Gordon, so you can use inverse Cartesian transform. You can basically map down that equation onto that PDE, onto ODE, on the velocity of the soliton. And then you can analyze that ODE. It has fixed points, and that's what you find. So you find that the soliton, the velocity of the kinks and the anti-kinks is proportional with, or it's like linear with the ratio between non-reciprocity and loss. Basically, what happens is that the more non-reciprocal you are, the faster your soliton wants to go, and it goes as fast as it can to dissipate all the energy you give it. Okay. After a while, it cannot go faster than the speed of sound. After this, there's a sonic boom, and then the radiations explode, and the system becomes unstable. Okay? If you do that experimentally, you find the same, but you also have a barrier below which, above which you have to drive your solitons and anti-solitons, and this is because of the discreteness of the system, because the elastic energy oscillates in time because of the discreteness of the system, so you have to make sure you inject enough to overcome that oscillation of the energy. Okay? Great. So that means you can actually now send trains of solitons and anti-solitons. And so here, so that means you can use that if you want as a mechanism to send, to do some nonlinear unidirectional wave guiding. Okay? So here we could transmit odd in the Morse code over our 50 units object. So that's nice. That's a mechanism to robustly transmit waves. Okay, great. I want now to, before I move on, I want to make a note about what's the difference actually between usually driven solitons and non-reciprocal solitons. And the difference is the following. So when you have a driven soliton, so it's this one, when your potential is tilted, basically you start from a symmetric potential, you add a constant force, and this tilts your potential, and that's really what it does. And then, if you have a soliton, basically this constant forcing here is this pink line, so you basically, it forces the field to go up. And so that's why here the solitons go up, but since it has a positive gradient here, when it goes up, actually it goes left, you see? But on the right, when you have an anti-soliton, so it goes up, but since the gradient is negative, when it goes up, it actually goes right. So you see here, that's why the soliton, when you drive the soliton with normal driving, you actually drive them apart, the solitons and anti-solitons. But here, we have a forcing that depends on the gradient, right? That doesn't derive from an energy potential. And the gradient here, you see, has a different sign on both the soliton and anti-soliton. That means that the soliton moves down, the anti-soliton moves up, but as a result, they all move right. Okay? And as you know, so in some sense here, I have a driving that's everywhere, so if I take my dominoes, I tilt the table, I have to tilt the whole table. But what you see here is that the active force is really local, right? It's really a local active force, so you can almost see the soliton as an active particle. It's really the soliton that creates itself its own driving, right? And the reason why, the topology of the soliton force, the existence of the domain will forces, let's say, a gradient of strain, and the gradient of strain is really what drives the soliton. So there's this kind of interplay between driving, between, the topological nature of the soliton and its driving. Okay, great. So a quick note, if you have solitons that are not topological, I think related to the talk you mentioned with Denis, actually it becomes much more difficult because you have to finely tune not only gain, you have to finely tune gain and loss, right? And so that means that, here I have weakly nonlinear waves, and if my non-reciprocity is too small, my solitons will die. If my non-reciprocity is too big, my solitons will blow up. But I have a very fine-tuned regime where I can send, when loss and gain precisely balance each other, and you can actually play the same games of soliton physics into scattering transform, and you can show that actually non-reciprocal, non-topological solitons are actually possible to see, but in a very minute region of parameter space. Okay, so if I want to make, let's say, a material like an analog starfish, I'd rather use topological soliton, right? Because it's much more robust. That's what we start to do with my PhD students, Rupesh Mawe and Xiaofei Yu, who was a PhD student in group. So we actually create analogs, we embed, we realize topological solitons in this metamaterial. We play a few tricks, and it's really preliminary data, but you can convince yourself that actually the reason why this object can crawl, and the reason why it can crawl is because you have a soliton traveling backwards in the air. Okay, great. So if you want, I guess the first result here is that you can reach an endless domino effect with topological solitons, and that could be a mechanism to create machines that could crawl by themselves. Okay, but if you look at nature, actually crawling is not the only thing nature does. You have this animal here that actually does more, and in fact, the reason why animals are so great is that it's not like if you think about locomotion, it's not that they can have one mode of locomotion or they are specifically very efficient at doing one thing, but it's because they can do many things, I guess. And like if you have only a single chain that can only do crawling, you're not as adaptive, let's say, as you might want to be as an active solid. So maybe the question we could ask is, okay, can we realize how to realize materials that do more than crawling? And specifically, if you want to do more than crawling, you need to go beyond actually one dimensions. Okay, and that's where the second project comes into play. So this was a project started long ago together with Vincenzo Vitelli and Colin, his former PhD student, and has now been brilliantly led by Jonas, also with the help of Jack Binish and Anton, both in the room. Okay, and the idea here is really to create to really connect this idea of non-reciprocity with shape-changing materials. And if you can connect the idea of shape-changing with non-reciprocity, then you can actually interact much more efficiently with the environment. Okay, and the most, so that's basically it. And let's see. And so this is just the same building block that we just configured slightly differently. Now instead of having pendula, we have linkages, right? And the linkage is basically the main component of a machine. And so you see here that is a non-reciprocal linkage, where if you push from the left, it opens on the right, but it closes on the right, but if you open on the right, it closes on the left. Okay? And you can use that linkage to construct materials. Okay? So the first thing you can do is make a, let's say, honeycomb, right? And so we actually put this object on our motors are not very strong, so we have to put them on an air table that flows air. And when it's passive, what do you expect from a single hexagon? If you tilt the table, the hexagon is compressed. If you tilt the other way, the hexagon is stretched. That's when it's passive. But now, if your linkages are non-reciprocal, and that's the same, sorry, here. So now I don't tilt the table like this, I tilt it like that. Right, so I tilt it like that, and here you see that you have a little bit of dilatancy effect, or pointing effect, if you wish, but the pointing effect is symmetric, right? But now, if I make my linkages non-reciprocal, I tilt my table, and this is going to be shearing in one direction, okay? And now I tell my table the other way, it's going to be shearing the other. Okay, great. So now you have a coupling between the two shear modes that compress the material shear. Okay, I mean, composites do that, right? When you're shearing upon compression. What's special about this, if I now shear it in the other, so I tip my table on the side, what you see, come on. Okay. If I tilt my table on the side, it actually extends, right? So compression leads to shear, but shear leads to extension. Okay, that's basically a non-reciprocal response between the two shear modes of the objects. Okay, you can actually do that also with the full lattice, and that's what we do here. When it's reciprocal, you know, you compress, it doesn't shear, or when you shear, it extends a little bit because of this pointing effect, but it's symmetrical. But now, if I turn on the elasticity, as I compress, it actually shears on the side, and as I shear, it actually extends now. Okay, so if I formulate this in the language of odd elasticity, formalism proposed by Vincenzo a few years back, you have actually a new odd elastic modulus that is asymmetric, that relates the two shear modes of the object non-reciprocally. Okay, you can actually measure that. And you can also devise a theory from the coarse grain, from the microscopy theory, and you can measure quantitatively actually the agreement, and it works. Okay, great. Great, cool. So that's nice. We have an active solid that has odd elasticity. This is not the first. Actually, Nicta starfish have been shown to actually do that. And actually, let's see. You also have other forms of active solid that don't display odd elasticity, but that's what the group of Olivier and also I think Gustavo is going to talk about this have shown. Actually, in those solids, what's interesting is not only they have non-symmetric couplings, but also generically limit cycles, dynamical solutions emerge. The difference between this and ours is that ours doesn't need momentum sources. Here you need a momentum source because they swim in the fluid, or here they crawl on the ground, but ours, they only have internal motors, right? So that means that we have, we can actually deploy those as a material, as a kind of robot, because we don't need to take always the momentum in the ground, right? So that's the main key difference, okay? And so that means you can start to do some experiments and see how the object interacts with the environment, right? So the first thing you can do is impact, and you see that depending on the sign on the reciprocity, you can deflect the impact. You can actually come up with a very basic theory, like a coarse grain, let's say, odd elastic theory. And what you see is that basically, you have inertia, elasticity, dissipation, and non-reciprocity here couples the two shear modes. And if you actually use that, you can actually predict the outcome of the impact. Okay. What you can also, and what it means is that what happens in the theory is that, like when your passive elasticity brings you back to the fixed point here at the origin, so you have isotropic force flow towards the center, but if you have non-reciprocity, it actually curls the force field, you see? Right? It curls, and then when you have an impact, it actually tends to follow the, right? And the same here in the other direction, okay? Right. But still here, we have only fixed point. The argument I want to make next is that when you have forces from the environment, that actually can completely change the picture, and only because of the force in the environment, dynamical solutions such as limit cycle can emerge. Okay, and that's what happens here. So here now I put my object onto a granular pile, right? I don't do anything special. It's just non-reciprocal. But then all of a sudden, it just spontaneously, whenever I switch non-reciprocity, it spontaneously starts to roll uphill. Okay, great. And so what you can do is actually revise the model that I showed before with the forces from the environment. It's a very basic assumption of the forces always pointing down, if you wish, and it assumes no slip boundary conditions and so on. But here you see that you have the nonlinear force here really comes from the environment. That's it, right? And so if you come back, and so the picture is the following, right? You have odd elastic material, you compress, because gravity compresses it, right? But then odd elasticity shears it, but because it's sheared, the center of mass actually now is above the contact point, so it topples over, right? That's this here. but because it topples over. But now it's in a new configuration, all the elasticity will actually shear it again. And now you see the center of mass again has moved beyond the contact point, poof, it topples over. And that's the most basic way of explaining the mechanism of how any elastic material, actually, that you put in contact with that is able to roll, we actually spontaneously roll. Okay? Great. If you actually do the math, what you can show is that, before we had a fixed pointed origin, but just this nonlinear force actually creates a limit cycle here. And you see that the force field here now points towards this limit cycle. So that means like whatever you do, you will robustly converge toward that limit cycle. You actually start spontaneously, you have a transient and so on. So that's actually when you compare it, the tools that people use in robotics. In robotics, what people do, especially in distributed robotics, they have to tell every single actuator what to do at every single time. So they have to be able to tell the actuator, okay, now you should accelerate. So that means they have to know, the robot has to know how fast it's going if it wants to be able to precisely time how when each actuator should do what. Here, somehow we have this emergent feedback loop between the shape of the object, and the shape of the object is really mediated by its elasticity, and the forces from the environment. And it's really, if you wish, so I guess the rolling gate and the limit cycle is really an emergent property of the fact we deploy that elastic object into another environment. Okay, it works. If you put it on a granular pile, you still have this limit cycle. So it will even if it's not perfect, it will always tend to follow the force fields here. Okay, great. You can play some games with that. You can deploy a full material here. It is a bit bulky, but it's also somehow able to accelerate. Now we put it on the treadmill again, and you see that it's actually able to go and to do it, right? And it will build up some momentum and go there, right? Right, great. And there's an extra ingredient here, is that the object, when we have this limit cycle that emerges because of odd elasticity and forces from the environment, but this one has many degrees of freedom, and you can also have additional nonlinearities that can actually drive the dynamics. And here, the nonlinearity that we have in our prototypes is really the fact that the motors saturate. So at some point, the motors, if you ask them too much, they're going to say, okay, no, now I stop. I don't do more torque. And so that means if you inject enough energy, you might have other secondary instabilities that emerge, and the system might just, visit other limit cycles. And so this one here is another limit cycle. When you put it on an inclined slope, it's not able to roll because the center of mass is not able to topple over the contact point. But actually, because of this extra cycle, it's actually able to now roll. Okay, so it goes. And what's also interesting is that it's adaptive, because if you now remove the slope and let the object crawl on a flat terrain, it's actually now it's able to roll. So we have now a material that decides by itself that it should crawl or it should roll because it has access to two distinct limit cycles in the dynamics. Okay. Okay, great. So where we want to go next is, if you increase the number of degrees of freedom and if you increase the dimensionality, you have access to more modes and more limit cycles. And I guess the one question is how do you explore those? So this is simulations, but we're also building, like larger scale, smaller prototypes where you can actually explore. Also, not only, like locomotion, but also pattern formation in there. And actually, what we see, we have also very interesting evidence of something that I'd like to call wave coarsening, where you have like all the elastic waves that travel and always tend to coarsen to the size of the system. So at the beginning, waves of small wavelengths tend to get amplified, and then progressively, as the amplitude builds up, they coarsen, they interact nonlinearly, they coarsen, right? It shows, I think, an example of a finite time singularity, and I think there's actually an interesting connection with wave turbulence here. We also go to 3D, so this is also our efforts to go to our 3D metamaterials. We don't have the experiments yet, but we also see this instance of wave coarsening in 3D simulations, where if
still go inverse in 3D. You said that it was going to large.
Yeah. It coarsens. if we wait, I'm not sure I have time to wait, but I'll show you later. But it corresponds and so on. And in 3D, you have, I mean, I guess if you want to really mimic, let's say a C star, you would have, now you see it starts to correspond. You would have to go actually to 3 dimensions, and there's very interesting questions in that area. Okay. So that's really where we're going. I think I want to make a little note about, why is active solid? People talk about active solids for a while now, but it's really, we don't have so many actually, examples of active solids, right? And I guess, from a synthetic, I'm a synthetic metamaterial guy, so I like to make stuff. And so for me, I foresee a lot of challenges in making and making sure there's enough energy and so on. But also I think maybe the question that connected very much to what Vincenzo said before is the control. How do you actually control these objects? It's extremely hard because, the action space of these objects blows up as you have many degrees of freedom. It's more robust as you have many degrees of freedom. You have more modes of locomotion, but the action space blows up. And so I think one of the next challenges is if you want to make a material that is able to toggle between different limit cycles and different modes of locomotion, we have this big challenge to actually overcome. And I'm going to skip. But that's what also we try to push with this idea of physical learning, which we now only do with fixed points and non-reciprocity, but not yet with limit cycles. But I'm going to skip that. Okay. And conclude. And conclude. So to conclude, I guess the main takeaway from my talk is that non-reciprocity is great if you want to create let's say, dynamical states that have an arrow of time. And that's very useful if you want to do cyclic functionalities, for instance, locomotion. But also it's very important when you think about these objects, about the dynamical steady states they have, that forces from the environment or influences from the environment actually can be key to actually controlling those dynamical states. And that will be different every time you do something different, whether you roll, you crawl, you jump, you do it in water at the small scale or the large scale. With that, I'd like to thank you and take any questions you may have. Thank you.
Thank you very much. So for questions, move to the microphone. So the first one, please.
Hi. Excellent talk. Very interesting. The solitons in the first half of the talk are connecting to vacua of a bistable system. I'm just curious if you've either built or simulated a system with a more complex vacuum structure, if that gives you, or if you, I'm just curious if you've looked at how does the complexity of dynamics increase as you have a more complicated structure of stable states?
Yeah, no, I think that's a good question. I think you can have other forms of multi-charge kings, for instance. You could have, multi-soliton structures, I think. In 2D, the things I showed you in 2D is also somehow something like that. Because here you don't have solitons, but you have topological defects, as you see here in the magnetic fields. So I think indeed, whenever however you shape your energy landscape will control in a large way, I guess, the structure of these waves. Yes. Yeah.
Hi there, awesome stuff, especially this question of robustness, because of course a biological organism needs robustness, because otherwise what it does in one thing is going to fail if it moves to another environment. Yeah. And so you showed the soft robot that uses soft compliance, I guess, to sort of impose some sort of robustness. But I was wondering if this wave coarsening also helps with robustness somehow, if some sort of emergence of long length scales, through injection of energy could get you there.
Yeah, well, the thing is, to me, I see this object as an object that has a multitude of limit cycles. The largest length scale is one limit cycle, or when you have a plus half defect, it's a limit cycle. Inside, it's a limit cycle, or minus half, it's a limit cycle. So the object has as many dynamical states possible. Here, I only studied, sliding on a glass plate, but whenever I deploy it in an environment, it might choose one or the other of the dynamical state. So it's principle. In principle, it has the ability of doing many different things, right? The only issue I have is, for now, is I cannot really control what it will do. I guess I rely more on serendipity, I guess, at the moment. Yeah.
Yeah. Thanks. That was a beautiful talk. So in these honeycomb lattices and so on, the ordelastic lattices, you could potentially have things like topologically protected modes or localized non-Hermitian skin modes and so on, even at the linearized level. So have you thought about, I mean, are they like a help or a hindrance, or can you do something?
Yeah, so this is gapless. This is, like there's no gap, there's no protected edge mode. But if you gap it, for instance, now we're gapping it with curvature, or you could also gap it by changing changing the structure inside. Yes, then typically, more often than not, you will see then edge modes that travel at the edge. Yeah. No.
Thanks for the talk. I had a question about the starfish, because so you have the soliton propagating, but does it propagate from the back of the starfish or from the center? And in that case, like, how do the different branches interact?
Yeah, I discovered that movie 2 weeks ago, so I wouldn't. I looked at it very hard, but I don't know. I think the starfish, we should ask Nikta, she knows much more about starfishes than I do, but has. But I think, so if we can look.
Everyone is acting individually. It has its own feedback control, its own autonomous way of acting. There is no way propagation whatsoever.
I think there is no. I don't know enough, but I think there is multiple ways in which the starfish can move, and in some way they can be simply entrained or synchronized by just the center of mass. So the center of mass simply somehow, makes them synchronize. I don't think there's a.
There's some cilia though that seems to be doing something.
Yeah. Yeah, these are like hydraulic feet, right? Yeah. But I think the way they synchronize is by mostly, as I understand, the center of mass, the way the center of mass moves. And depending on how the center of mass moves, they might synchronize with traveling or like metachronal wave, as people call them, or simply just all at once. I think they have different modes of locomotion, but I'm not the expert, I guess.
Yeah, thanks. Beautiful talk. Can you crystallize for me what the exact role is of non-reciprocal interactions as opposed to just feedback in these systems? Because these get mixed together in some way.
Non-reciprocity is, at least we implement it with feedback. You need not implement it with feedback. People in optomechanics, they shoot lasers very timely with like lag times very carefully engineered. But the way we do it is through feedback. And of course, there's many other types of feedback you could use. Right? And I think, in fact, that was a question I had for Vincenzo. Like, if you had for instance, negative damping, like a negative pendulum with a negative damping, you also can have limit cycle. It's a van der Pol limit cycle. So, to me, if you want to, I guess that's an open question. What kind of feedback do you need? Is negative damping enough, for instance, to get you what you want? It seems like the non-reciprocity is useful if you want a sense of an hour of time in general, I guess. Yeah. Capizza is hard because it's time modulation, so you have to very carefully synchronize, how you do it.
Those systems, do they have already a natural frequency?
Yes.
But
yes.
That you don't want.
No, you don't want, because then you have a synchronization challenge, right? And so time modulation.
Because it doesn't make any sense to create something that you already have. This is what we were discussing, Christian. If you do something viscoelastic, you don't want the elasticity already to exist. And the second thing that you would have also in the question here is that you need the way that whatever viscosity or material property.
So to follow up on that particular thing, so I think so. It seems like what Christina says. Once you have your viscoelastic, you have feedback, you have delay, you can get, I think, almost everything except the arrow of time. Is that correct? With how you're seeing this?
Plasticity without plasticity doesn't do the trick, because you need whatever viscosity coefficient to change in real time as you change the physical degrees of freedom. This is not generic. It can happen, but it's not generic. And it has to...
No. So I think to...
No. You can have an elastic moduli, so you can have a G prime and G double prime.
And it's maybe it's better.
But whatever transition has to be updated when you change the material.
So Vincenzo, I suggest we organize at some point a round table around these several ingredients and what each do. I think that would be really interesting. But let's, since we don't have much time for the follow-up questions, let's move back to the questions.
Hi, I'll be brief. Thanks for the talk. It was great. You showed us like some very interesting topological defect behavior, and I was wondering, like in passive system, for example, the forces between defects have a certain sign which is fixed. Mm-hmm. In active systems, there's some examples where these forces can change based on the sign of the activity. Did you calculate, or did you see maybe the interaction between the forces between the defects, or?
We started to do that, but the point is when you look at the way people calculate forces between defects, they use free energy. Right. And that even in active nematics, people do that somehow. They do some magic, and then it maps to a free energy. People like Luca Jomi did that. But here, without elasticity, it's not so easy because you don't have an energy function to start from. So all that bags of tricks you could use is actually not so straightforward.
I understand, but maybe, for example, even from the trajectories, you can kind of see, if they, at least the sign, if they're pulling.
So charges opposite charges will attract, and same charges will repel. Okay. But in terms of the mobility, and also like up. I can show you. I can't. I never get tired of that movie, I guess. But and I think that maybe it's hard to see, but plus half defects and minus half defects also have a different chirality around them. Okay. So not only the defects have a mobility, but they also have a kind of a gear-like motion. And this is very much open. We haven't. Okay.
Thank you.
Thank you for your great talk. I have a question regarding how a robotic material or robotic system can change the environment for the following reasons. Mm-hmm. So from your continuous equation, the advective term coming from this non-reciprocity remind me of bacterial chemotaxis, where the bacteria population, let's say, produces chemoattractant that leads to self-generated gradient, which leads to self-generated attraction. Similarly, in the starfish or let's say the centipede locomotion, we can imagine a situation where the fish are, let's say, secreting some, let's say, chemicals that can also lead to some self-generated advection term, which can have this term, non-reciprocal effect. And I was wondering whether you can have similar situation in robotics where your robotic system can actually change the environment that leads to this effective non-reciprocity and the advective term.
Yeah. So I guess the main difference between our materials and the things you're referring to is that the sensing, our materials only sense the environment through their deformations. There's no sensing of a light field or like a, but you could, I mean, I guess you could ask whether you could do that. You could add ingredients to your robots. I mean, for instance, if you want to leave like a scent or like a trace of where you've been, you could ask if you deploy this on a granular medium, for instance, and if the object plows through the granular medium, then you would leave like a trace of where it's been, right? So I could see an analog here without doing anything to my system that would go towards what you do. I could also put light sensors or things like that also to do more elaborate external sensing as well, right? And then I think we could ask the very same questions as well.
Thank you.
Okay, so I think we run out of questions, so maybe let me add the final one. So in all these systems, you always have inertia, right? So yes. The waves are naturally there, because they are essentially elastic inertial system. Yeah. But then it's the property of those waves that are bizarre or odd because of the non-reciprocity, right?
Yes.
Okay, so in overdamped situation, none of this would take place, or what would be the situation?
No, in overdamped situation, those waves will be underdamped. Actually, odd elasticity gives you waves, but the waves are underdamped. Underdamped, or overdamped. No, not overdamped. They oscillate and then.
Yes, they oscillate. Okay. They are damped, but on a certain time scale.
But I think you might have additional instabilities that emerge. So if you crank up the gain enough, or if you do something specific, especially with the bulk modulus, I think you can have. But this is really in the paper of Vincenzo. You can.
To some extent,
or maybe through nonlinear forces from the environment, right?
Okay, so I think we can thank our two speakers.
I had one more question.
There's one more question.
Sorry, is this mic on? Yes. So I had a question that's maybe also for Vincenzo, which is the question of capacity in terms of limit cycles. So can we say anything generic about how many limit cycles these systems have, and maybe also how many limit cycles they can learn? I mean, that would be the obvious analogy to the Hopfield model. Do we know anything about that, or do you see any way of making progress?
For me, I would say, like a system with 2 degrees of freedom can have 1 limit cycle. So if you have n degrees of freedom, you can have, n over 2 limit cycles, I guess. But the question is whether they do anything that you want, right? That's, I guess, my take, and it's hard. To answer the question is hard, I think. Yeah.
So I cannot give you a full answer because this is something we're working on, but I think that this question is particularly relevant in the case of the spin graph. When we make the J random quantity, our first indication is that this will be strongly dependent on the protocol that you use. And of course, I mean, part of the trick is to construct algorithms that optimize that quantity. But it is possible. And how it scales, of course, with the...
Okay, thanks.
Use the mic. Use the mic.
To count limit cycles, why not considering the Poincaré-Bendixson? Because, for instance, in your phase space, you have an attracting limit cycle on a 2-dimensional phase space, stationary, so then there you can use it. And you can have some conditions on at least understanding, can there be a limit cycle? Yeah.
I think at this point we don't have yet multiply coexisting limit cycles at the same time. Or we have 2, right? And in that case, I guess doing what you propose is meaningful. But maybe the question is how to expand it to more like even more dimensions of phase space, right? I think you can do that, maybe that argument in two-dimensional phase spaces, but how do you do if you have a phase space that's n, right?
But for instance, in your, just a mini follow-up, in your equation for S1 dot, S2 dot that you had, do people try to look at, for instance, how attracting are these limit cycles? Because there you can sort of understand the stable manifolds of the limit cycle. There are many metrics that you can sort of use. For instance, so the last term is going to give you the limit cycle because it's the only nonlinearity you have. And then you can say, for instance, if I take the divergence of this equation to be an attracting limit cycle, I have to squeeze phase space. So do people use this kind of thinking or techniques to design your system, or not yet?
We don't, but I'd like to. To me, that's something that's very interesting because at the end of the day, you would want to somehow map, all the possible attractors you have. I think, right?
Okay, so let's thank again our speaker for this morning session. We come back in half an hour for 2 more talks starting at 11 sharp, please.